You know, there are these absolute giants hiding in plain sight, the unseen powerhouses of our modern world. I'm talking about industrial boilers. These massive systems are really the heart of everything, from power plants to refineries, and they do one thing incredibly well: turn simple water into high-energy steam. So, the question is, how do they do it safely? Let's dive in.
And really, this is the fundamental question, isn't it? This is where it all begins. We're dealing with temperatures and pressures that are just mind-boggling. So the engineering here isn't just about creating power, it's about containing it. That single challenge, how to stop it from going catastrophically wrong, is at the core of every single design decision we're about to explore.
So, to understand how these systems really work, we first have to look at the two foundational designs. Every industrial boiler out there is built on one of these two principles. It's a simple but pretty brilliant difference in how you approach the problem. And here they are, side by side. In a fire tube boiler, hot gases from the furnace literally flow through a bunch of tubes that are surrounded by water. Now, in a water tube boiler, you guessed it, it's the exact opposite. Water flows through the tubes, and they're heated by the hot gases all around them. A simple flip, but with massive, massive implications.
And see, that one design choice, it changes everything. Fire tube boilers, they're great for lower pressure stuff, smaller jobs. But for the massive loads you see in an industrial power plant, the high-pressure water tube design is king, no contest. And that's the one we're going to focus on, which is governed by the super strict safety rulebook known as ASME Section I.
Okay, so let's follow a single drop of water on its incredible journey. We're going to trace its path as it transforms from just cool liquid into high-energy, superheated steam, which is basically the lifeblood of the entire facility.
This is our roadmap. First, the feed water gets a preheating boost in what's called the economizer. Then, it flows into these tubes called risers, and that's where it actually boils. The steam and water mix that comes out of there then rises up to a separation drum, and finally, that pure steam gets superheated to squeeze out every last bit of energy.
Now, before we go any further, just look at this. This formula. This is the absolute bedrock of boiler safety. It calculates the minimum thickness, T, that the steel shell needs to be to contain the immense pressure, P. And the most important part? This calculation is required by safety codes to ensure the structure has a safety factor of at least 4. That means it's built to withstand 4 times its normal operating pressure. That is completely non-negotiable.
All right, let's zoom in on what I think is the most important component in the whole system, the steam drum. This is where the steam quality gets perfected, and it's where the most critical safety systems are located.
You might think this drum is just an empty tank, but no way. Inside, there's this complex maze of baffles and cyclone separators. As that wet, steamy mixture rushes in, these parts use physics to literally spin the heavy water droplets out, leaving only pure, dry steam to exit the top. This is absolutely essential for efficiency and for protecting equipment down the line, like the turbines.
And this number, this just brilliantly illustrates the obsession with safety. 2. That is the absolute minimum number of safety relief valves required by the ASME code on any power boiler. So why 2? Redundancy, plain and simple. If one fails, there is always a backup. And here's the powerful logic behind that rule. The combined capacity of those valves has to be able to vent steam faster than the boiler could ever possibly generate it, even at full blast. This makes sure that even in a worst-case scenario, the pressure can never, ever build to the point of an explosion. The valves will always win that race. Okay, let's switch gears a bit to system health. A boiler is this dynamic thing that needs constant attention to stay healthy. So we'll look at how engineers keep it clean and, what happens when things start to go wrong.
Think about it. As water turns to steam, all the minerals and junk get left behind, and they just get more and more concentrated over time. So this process, called blowdown, is like a scheduled cleaning. A valve opens up to drain off some of this concentrated, gunky water, and it's replaced with fresh feed water. That's how you keep the system healthy and prevent damaging scale from building up inside.
But what happens if you neglect that? Well, it's a domino effect. It starts with internal scaling. This gunk acts like insulation, right? So it chokes the heat transfer, forcing the system to work harder and just waste fuel. Even worse, that scaling can lead to hot spots, causing the steel tubes to soften and form these dangerous bulges. And if that bulge gives way, that's when you get a tube rupture and a sudden, massive drop in system pressure. So let's bring it all together. We've seen the parts, we've seen the processes.
Now let's look at the engineer's blueprint, the key calculations that really govern everything, from the initial design to the day-to-day operation.
First up, the power output equation. This formula tells engineers exactly how much steam they can make based on the heat they're putting in and the boiler's overall efficiency. It's the most basic measure of the boiler's performance.
Second, well, here's our friend from earlier, the shell thickness formula. This is the one that dictates the physical strength of the whole vessel, making sure it can safely handle the incredible forces at work. This is the heart of structural safety. Third, we've got the blowdown calculation. This is what helps operators manage the water purity. It tells them exactly how much water they need to drain to stop that damaging scale from building up and to maintain the system's long-term health.
And finally, the relief valve sizing formula. This calculation is so critical. It determines just how big those safety valves need to be, making sure their total capacity can handle the absolute maximum steam flow possible. This is the ultimate safety net against a catastrophic overpressure event.
So when you put it all together, from its core design to its safety valves and all the math behind it, every single part of an industrial boiler is a calculated piece of engineering. It's a whole system designed to harness these incredible forces, safely and reliably. It really makes you wonder, what other essential, complex engineering marvels are just hiding out there in plain sight all around us? Thanks for watching.